Good day and welcome back to part 3 of our discussion of double integrals and polar coordinates. So as a reminder, one of the standard types of problems that we will encounter and continue to encounter is where we ask you to find the volume of some solid which we have described. So in this case, it's going to be the solid bounded by the surface z equals the square root of x squared plus y squared, and x squared plus y squared equals 4, restricted to the first octant. And my first step towards this problem of setting up a double integral to represent this volume is to sketch, at least roughly, what this solid will look like. So let me think of a few words to describe these surfaces. So for z equals the square root of x squared plus y squared, thinking back to our quadric surfaces section, is there one word you would use to describe that surface? And it's the cone, the top half of the cone. So if we wanted to sketch what that cone would look like, it's a cone that comes down to a point at the origin, and because it's z equals, it wraps around the origin. Similarly, what's one word you would use to describe the second surface? And if you said cylinder, I agree. And note, cylinders, cones, paraboloids, spheres, these are all surfaces we're going to want to be able to very quickly and efficiently recognize. So that cylinder, x squared plus y squared equals 4, wraps around the z-axis. That z equals 0 trace, i.e. what you get in the xy plane, would be a circle of radius 2 centered at the origin. So roughly speaking, something of the form seen here. Now is the fun part. From this cone and cylinder, can we somehow determine what is the solid that is bounded, who has a finite volume that we can calculate? And just having the cone and the cylinder is most definitely not enough, because it could be underneath the cone and in the cylinder, or above the cone and in the cylinder. But in either case, we're talking about a solid that encloses an infinite amount of area. That's not what we're looking for. But we are restricting this to the first quadrant. So if we picture this a bit more clearly in the first quadrant, we have the cone. And note, this is just the portion in the first quadrant. And we also have the cylinder. And now I think we can more clearly see the enclosed volume. So it's bounded below by the z equals 0 plane, it's bounded above by the cone, and you lie inside the cylinder. That is, we can think of this region D that we see in the xy plane as the region we would evaluate a double integral over. So the volume is going to be the double integral over that region D. And remember how we set up this volume integral. We take whatever the larger surface is, so upper, and we subtract away from that the smaller surface. So in this case, our larger surface, the thing that bounds this region on top, is the cone. So that would be the square root of x squared plus y squared. And the lower surface, the thing that bounds us below, is simply the z equals 0 plane. So minus 0 dA. And at this point, there's really nothing new, at least in terms of polar coordinates. It's just setting up this double integral that would represent the volume of the solid. The new part is just realizing that this region of integration is something that's highly conducive to polar coordinates. So it's a circle of radius 2, which is making up our region D, specifically the portion in the first quadrant. And this is one of those so-called polar rectangles. So note the R values are varying from 0 to 2. 0 is at the origin. You can go all the way until you hit r equals 2. And the theta values are varying from theta equals 0, which would correspond to that horizontal axis, up to we hit theta equals pi over 2. So converting into polar coordinates, note x squared plus y squared is really r squared, and the square root of r squared becomes r. While dA is r dr d theta, our r values vary from 0 to 2, and our theta values from 0 to pi over 2. And let me just note, getting it to this point is really what I consider to be the new part of the problem. In order to evaluate, we can make the same observation we've made in our previous few examples. You can immediately break this up into two single integrals multiplied together, because our integrand function, r squared times 1, is a function of just r multiplied by a function of just theta. So if you anti-differentiate 1 on the interval from 0 to pi over 2, you get back pi over 2. The antiderivative of r squared is 1/3 r cubed, from 0 to 2, so we substitute in 2, we put a minus sign, we substitute in 8. And you can most definitely leave this as 8 pi over 6, and there's certainly nothing wrong with writing it as 4 pi over 3. And it's always worth kind of observing what our work should look like. When you turn something in for, say, homework and then eventually on exams, you should, to the best of your ability, sketch the solid, whose volume we are calculating, and in a separate xy coordinate system, that region of integration D. Once you have those two things sketched, we should set up our double integral and evaluate and make sure that we're using good proper notation at each step along the way. Let's move on to a second example. We will evaluate the given double integral. And note, once again, the question will most likely be phrased exactly in this form. We simply ask you to evaluate. The observation for us to make is that this is something that's highly convenient for us to describe in polar coordinates. So let's go ahead and sketch this region of integration, which is excellent practice. So note, working our way from the outside in, the y values are varying from 0 to 1. And remember to note that the y values are varying from 0 to 1. That is giving us kind of this horizontal strip, which is where our region will be located. Now for a value of y between 0 and 1, we need to think, how do those corresponding x values vary? Those corresponding x values vary from x equals y to x equals the square root of 2 minus y squared. So a few observations. Note x equals y is a standard line, slope 1, going through the origin. Additionally, x equals the square root of 2 minus y squared is something that I'm hoping we're starting to recognize more quickly, and that would be a circle, at least in this case the right half of a circle, of radius square root 2 centered at the origin. So this would be the graph of x equals the square root of 2 minus y squared. So for a y value between 0 and 1, our x values vary from the line x equals y over to this semicircle of radius square root 2. And note, this is in fact a polar rectangle, because in polar coordinates we could note that we're bounded kind of below in theta values by 0, and we go into this line y equals x. And in terms of theta values, that's an angle of 45 degrees, or pi over 4 radians. And the outside circle is a circle of radius square root 2 centered at the origin. So in terms of polar coordinates, we could describe this as a rectangle with the r values between 0 and square root 2, and the theta values between 0 and pi over 4. And I'm not going to actually go through all of the details to evaluate. I'm just going to simply convert this Cartesian integral into polar coordinates. So our starting integral would be from 0 to 1, y to square root of 2 minus y squared, and we're integrating x squared dx dy. In polar coordinates, remember x squared will be replaced with an r cosine theta squared. Dx dy becomes r dr d theta. We have r on the inside varying from 0 to square root 2, and theta on the outside varying from 0 to pi over 4. And this is the equivalent double integral in polar coordinates. And I know I said we would just write this down, but for good practice, let's go ahead and evaluate the integral as well. So once again, we can break this up into an integral in terms of theta multiplied by another single integral in terms of r. So the integral from 0 to pi over 4 of cosine squared of theta multiplied by the integral from 0 to square root 2 of r cubed dr. Note we have an r squared times r to make it an r cubed. And I think the integral that's worth spending a moment on is reminding ourselves how to integrate cosine squared and similarly sine squared. And in order to integrate either one of those trig functions squared, we need to remember a trig identity that makes the integral easier for us to evaluate. So as a reminder, cosine squared theta is 1/2 the quantity 1 plus cosine 2 theta. So we either think of this as a half angle formula, or you could maybe think of it as a double angle formula for cosine. Similarly, sine squared is 1/2 1 minus cosine of 2 theta. And if you want to integrate cosine squared or sine squared, we rewrite in terms of these identities. So for the cosine squared, we can pull 1/2 out, and we're integrating from 0 to pi over 4 of 1 plus cosine of 2 theta. And I usually just take care of a single integral at a time, but then at each step along the way, I'll leave space to fill in as we evaluate the second integral. So the antiderivative would be theta plus 1/2 sine of 2 theta. And this is from 0 to pi over 4. And I'll note if you don't see that antiderivative, it's something that hopefully you will after practicing a bit more, but you could do a substitution, let u equal 2 theta. But since this is something that we encounter frequently, I'll typically just kind of write down that antiderivative when it's possible. So we substitute in pi over 4. So 2 sine pi over 4 would be pi over 2. And then we subtract away what we get when we plug in 0. And note, sine of pi over 2 is 1. So what we end up with is pi over 4 plus 1/2 quantity times 1/2. So we can write this as pi over 8 plus 1/4. And remember, this is only half the problem, so to speak. We also had this integral in terms of r values to take care of. So going back and filling in these details, the antiderivative of r cubed is 1/4 r to the 4th from 0 to square root 2. So if we plug in the square root of 2, minus sign, plug in 0. And note, the square root of 2 raised to the 4th power is really 2 squared. So 4 divided by 4. So 1/4 times 4, which gives us the pi over 8 plus 1/4. That finishes up the material in this video. And this is a point where if we were meeting face-to-face in class, I would be handing you all a worksheet dealing with double integrals in general, asking you to spend a bit of time working through it. So you can find that worksheet on Canvas underneath the videos for this section. I strongly encourage you to take 25-30 minutes, work through those examples. Then in the next video, we'll go over the first problem. And you can also find full solutions posted on Canvas to check versus the rest of your work. So stay tuned and take care.